Hello and welcome back to my channel. Today we will be presenting the part 2 of the ongoing series on visibility of divisibility. So we have already seen the part 1, and there we have seen that is a given number, whether it's divisible by the prime p. What we do basically is we extract a much smaller number c from the given number s, where of course c can be expressed in terms of the digits of the original number s, and the rules demand that if that smaller number c, if divisible by p, then also s is divisible by p. So we have seen the popular tests for prime p equal to 2 or 5, 3 or 9 and 11, which are available in class 4 or 5 textbook, right? And then we presented a device which we call strategy 1 to see that whether there is possible that there is some common single recipe which gives all these tests which are apparently different from each other. And we have seen that yes, for the A's, how to extract that C. C is simply the summation, where AI are the digits of the number and MI are the multipliers, and which are nothing but the remainder when 10 minus P to the power I is divided by, as simple as that. So that was the recipe, and we have applied for different numbers. But in part 1, we have left some unanswered questions, and they are addressed here in part 2 video. Say for example, the question was that what about the popular divisibility test for p equal to 7, that we have not seen in the part 1, and whether we can apply our device strategy 1 for, we can say, test 4, that is for prime 7. Can we apply? And more importantly, how that strategy 1 that we presented in the part 1 works. So what is the mathematical rationale behind the strategy 1? So this will be answered. Well, let us first see what is the popular test for 7. It is like the s, the number you are given, you remove the last digit of the number and double it, and then subtract that amount from the remaining number. And if that number is either 0 or a small number which is divisible by 7, if it is yes, then the given number is divisible by 7, otherwise no. So that is the recipe for p equal to 7. That means, mathematically, more precisely, we are defining c as n minus 2 a0, where n is the truncated number from s that you are getting after dropping the last digit a0, and that n and we subtract twice of the a0 from that truncated number, and if that is divisible by 7, then s is divisible by 7. Well, let us see an example. The 154. So truncated number is 15. If you drop the last digit 4 a0 and then make it twice, so 2 into 4, and you subtract it from the truncated number n, that is 15. So 15 minus 8 is 7. So 7 is divisible by 7. So 154 is also divisible by 7. So this is the example. Well, now we are going to apply strategy 1 for p equals to 7, that we have already done for other prime numbers 2, 3, 5, 11. So here the recipe that we have to find the mi, the multipliers, and the multipliers are nothing but 10 minus p to the power I divided by its remainder, right? So here p is 7, so 10 minus p is 3, so mi is remainder of 3 to the power I by for I equals to 0, 1, 2 up to n. Okay. Now let us see one by one. What is the m0 value? So 3 to the power 0 by 7, its remainder is 1, as you see. And what is M1? 3 to the power 1 by 7, so remainder is 3. M2, 3 to the power 2 by 7, remainder is 2, because 3 to the power 2 is 9 divided by 7, so 2 is remainder. Similarly, M3, 3 to the power 3 by 7, its remainder is 6. M4, again the remainder is 4, we can check. M5 is 5. So, if you stop here, we can say that for I equal to 0 through 5, the MI values are 1, 3, 2, 6, 4, 5. So, that much you have to remember, that 1, 3, 2, 6, 4, 5. Okay. Now, let us see a quick example. Say for example, 3-digit number. So, what would be your C? MI, AI, and MI is, okay, 1, 3, 2, 0, 1, 2, I. So, 1, 3, 2 in red color, okay, and multiplied by the corresponding A0, A1. So, similarly, if you go for a 4-digit number, then it is again 1, 3, 2 and 6. So, here 6 is coming as M3, and example 133. So, you have to have 1, 3, 2. So, in red color 1, 3, 2 and multiplied by A0, A1, A2. So, A0, 3, 3, 1 from right to left. So, you get 3, 3, 1. So, sum over MI, AI gives you actually this summation, and that gives you 14. Another example, if you take 142. So, 142, again it's 1, 3 and 2 red color, and the A0, A1, A2 is 2, 4, 1. So, 2, 4, 1 and that gives you 16. So, clearly we see that the first one 14 is divisible by 7, but 16 is not. So, our conclusion is that 133 is divisible by 7, but 142 is not divisible by 7. So, it is as simple as that. But if you take a slightly bigger number, say 5-digit number, then you have to take M0 to M4. So, 1, 3, 2, 6, 4. So, you see 1, 3, 2, 6, 4. And the A0 to A4 is 25191. So, 25191. And if you sum up, you get 7, which is divisible by 7. So, we can declare that the given number, this one is also divisible by 7. So, that way you can apply it even for a bigger. Okay. What about a really big number? That means if the number of digits is more than 6. With M5, you can handle up to 6 digits. But if it is greater than 6, 7 digits, 8 digits, 9 digits, then you need actually I greater than. So, what you do? Interestingly, for I greater than 5, of course, you need to calculate MI. But interestingly, this MI are nothing but the repeating values of the earlier. That is, MI is 1, 3, 2, 6, 4 and 5 for I equal to 0 to 5, and then MI is again this 1, 3, 2, 6, 4 and 5 for I equal to, it was 5, so from 6 through 11, and exactly these are the repeats, and you can check it on your own, and so on. That means even if you think of a bigger number, you can get the same repetition. So, we really don't need to remember a lot of numbers or digits. Okay. So, let us see a quick example. Here is listed in a systematic way, that for I equal to 0 to 11, the red color 1, 3, 2, 6, 4, 5, and then repeated again the blue, green color 1, 3, 2, 6, 4. Okay. So, let us really see a big number. Okay, 12 digit. That means n equal to 11. 0 to 11 means 12 digit. So, what we will do in general? We will use this red colored 1, 3, 2, 6, 4, 5. That is the MI values, and then I equal to 6 onwards. You use the green one, but they are again the same. So 1, 3, 2, 6, 4, 5. Okay. Let us take a real example. Suppose this is the given number, quite a big, right? Quite a big. Now what we will do? We will simply sum. So again you see 1, 3, 2, 6, 4, 5 red color, and again repeated 1, 3, 2, 6, 4, 5, and the digits are from right to left, A0, A1, A2, etc. So 7, 1, 6, 6, 5, 7, 1, 6, 6, 5, then again 7, 7, then 2, 7, 7, 1, 7, 1, 2, 7, 7, 1, 7. Okay. So if you do the sum, you will get 189. And even if you are not happy that it's quite a big number, 189, then you can again apply the same formula, the same strategy for 189, and this time it would be simply, well, you see that M top and M bottom are same, so red color and green, right? Here red color. Well, if you want to apply again that strategy for 189, you can. In that case, it is simply the first three MI 1, 3, 2. So it is simply 1, 3, 2, and the digits are A0, A1, A2 is 9, 8, 1. So 9, 8, 1, and you get this 35. Now we can easily check that 35 is divisible by 7. So the number 189 is divisible by 7, and since 189 is divisible by 7, so the big number S is also divisible by 7. So are you happy? Fine. So here is the table just listed that we have already done in the last video for p equal to 2, 3, 5, and today we have done for 7. That's why it's red colored. And we have done 9, though 9 is not a prime. 9, 11, and today we have listed only. We can check that for 13 you can apply, and similarly you can apply for any p in general. 30, 13, you will get this series up to I up to M5, and you can go on for higher number, and we can check that number 117. So you use that M0 1 minus 39 etc. 1 minus 39 etc. and you will get the value 13. And 13 is divisible by 13, of course. So S117 is also divisible, right? Now let us take a very interesting puzzle. The puzzle goes like, any 6-digit number consisting of all 6 equal figures are divisible by 7. What is that equal figure is not important, but if they all are equal, all the 6 digits of a 6-digit number, then the whole number is divisible by 7. So we can easily check by applying our strategy 1. How? Here I list again that for I equal to 0 to 5, the MI value is 1, 3, 2, 6, 4, 5. Now S is a number whose all 6 digits are same, A. So C is nothing but 1 into A plus 3 into A plus 2 into A and so on, 6 into A, 4 into A, right? And that gives you actually 21A. Of course, you can see that 21A is divisible by 7. So the original number S is also divisible by 7. So that's how our strategy 1 answers this interesting famous puzzle. Now the most important part of today's video, why or how does this strategy 1 work? We will justify why the C formula looks like this, right? This is quite mathematical and logical. So let us try in our own way. Suppose S is the number, so A0 to AN, these are the digits in unit place, 10 place, 100 place, etc. So in decimal number system, this S can be represented as 10 to the power I, A, as you know, I is 0 to n. So that is the number system problem that you know, everyone. Now the trick is that let us take 10 as P plus M. P is the prime, constant prime. For example, P is 2, then M is 8, P is 7, M is 3, and so on. Okay. Now we can write this S is 10 to the power I and 10 is P plus M. So we can write S is P plus M to the power I, A, I. Now you can use your mathematical preliminary knowledge, you can say, that is binomial expansion. For what? For P plus M to the power I. So p plus m to the power I by binomial expansion is this sum over j 0 to I, and ICJ the binomial expansion coefficient, and p to the power I minus j and m. So a plus b whole square is a square plus 2ab plus b square actually fits in this one, or even a plus b whole cube or a plus b any to the power I that we get from this one. This is called binomial expansion. Okay, so this is sum over j. Now inside this p plus m to the power I, a summation j comes, summation over j, and already a sum over I is there. So it's a double sum, I 0 to n and j 0 to I, and this quantity. Okay. Now another trick. Let us split this double sum into two parts. One is I greater than j, and another is I equal to. That means when this is I equal to j, the last single part, that means the other part contains j equal to 0 to I minus 1, and another part, this summation sign is not there because it is simply j equal to I. So we split into two parts. One is as usual, only the index is changing. J is 0 to I, and here it becomes j to 0 to I minus 1. And in other part, the single sum over I is there, but not j, because it is a single term for j is equal to I. So it becomes ICJ becomes ICI. So ICI. P to the power I minus j becomes p to the power I minus I, and m to the power j becomes m to the power I, and aj becomes a. So these are the two parts. Now interestingly, okay, you can think of that. What about this term? ICI is actually 1, and p to the power I minus I is p to the power 0, that means 1. So only m to the power ai is remaining in the last. Okay. So this is the two part of the whole expression. Now interestingly, you have to note that in the first term, p to the power I minus j and I is greater than j. That means in each of this term, p or some power of p is there. So this part is divisible by p. So that means the left hand side first part is divisible by p. So we can write that S is nothing but a part that is divisible by p plus some other part I equal to n to 0 mi m to the power I ai m to the power. Okay. So here again I am repeating. So S is the first part divisible by p plus m to the power I ai. Okay. So we are very close to our solution. Again we have to play a trick. Suppose that this m to the power I, whatever it is, if you try to divide it by p, you will get di with some remainder, maybe mi. That means m to the power I can be thought of di times p plus mi. So m to the power I is di p plus m. That means mi is the remainder when this m to the power I is divided by p, and mi is the remainder. Okay, in other words. So we are defining clearly what mi is, remainder when m to the power I is divided by p. And of course, you can easily check that di is 0 or positive integer, but mi can be 0 or both positive and negative. Therefore, we can say that S is the first part divisible by p, and then this m to the power I we have taken as dip plus mi. So dip plus mi into ai into a. Okay. So two terms are there. So again we can separate these two terms like this. So the first part, and then I equals to 0 to n dip part into ai, and the last part is sum over 0 to n mi into ai. So now I think we are a bit excited to see that the second part of this summation, this red color, it contains p, right? And whatever the di and ai values are, it contains p, so it is divisible by p. So the second part is also divisible by p, and remaining part is also divisible. So we can say that what we get finally, that the first part, the second part, both are divisible by P. So S would be divisible, and it requires that if Mi Ai is divisible, right? And that is exactly the demand of our strategy, that C must be such that Mi Ai, that if this is divisible, then all the three parts are divisible. That means S is. So that's how we get the mathematical rationale behind our strategy to find the C part from S. Okay. But still, some questions remain unanswered. First of all, is there any other general strategy we can call strategy 2? Because you see that strategy 1, when applied to P equal to 7, we have not got the popular test. Rather, we have got something else which works fine, even for 12-digit number we have seen, but it is not the popular. So that actually gives a clue to this question, that is there any other generalized strategy, strategy 2? And if it is there, how does it work? And does it lead to the popular test for P equal to 7? So, and moreover, is it applicable for any P in general? So these are the questions to be answered, and all will be coming up in the next video, visibility of divisibility part 3. And till then, thanks for watching. I will be happy if you please come back for the part 3 video with some comments maybe. Thank you once again.